For decades, the design of Star Trek's U.S.S. Enterprise was widely viewed as a stylistic choice rather than a scientific one. Its flat saucer, extended hull, and widely spaced warp nacelles became iconic, but few assumed the design reflected real physical constraints. Recently, however, new theoretical work in warp drive physics has suggested otherwise. Scientists revisiting how spacetime could be manipulated for faster-than-light travel argue that engine placement and field geometry are central to the problem. This has renewed attention on how science fiction and real physics sometimes converge. In this video, we will examine what scientists found, why it matters, and what it could mean next. Let's get started. The renewed interest in the Enterprise's design stems from recent theoretical studies focused on warp drive concepts within the limits of known physics. These studies do not claim that faster-than-light travel has been achieved, but they revisit how spacetime might be engineered rather than how a spacecraft might be propelled. The foundation of this work traces back to the early 1990s, when physicist Miguel Alcubierre proposed a mathematical solution showing that faster-than-light travel could theoretically occur without violating Einstein's theory of relativity. In this model, a spacecraft would not move faster than light through space. Instead, spacetime itself would be distorted, compressed in front of the vessel and expanded behind it, allowing the craft to traverse vast distances while remaining stationary within its local spacetime. While Alcubierre's equations were mathematically valid, the model faced immediate challenges. It required extreme physical conditions and relied on a continuous, torus-shaped warp bubble surrounding the spacecraft. This geometry proved difficult to analyze and raised questions about whether such a structure could ever exist in a physically meaningful way. Recent research revisiting these ideas has taken a different approach by focusing on the geometry of spacetime distortion rather than treating the warp bubble as a single, unified structure. Instead of one continuous field, researchers explored whether multiple, spatially separated warp field generators could collectively shape spacetime. This shift produced a key insight. When spacetime distortion is generated from separate points rather than a single enclosing bubble, the resulting geometry becomes easier to model and conceptually more stable. Importantly, this configuration places the field generators away from the inhabited portion of the spacecraft. When visualized, this arrangement strongly resembles the twin warp nacelles of the U.S.S. Enterprise. According to researchers involved in this work, the resemblance reflects an underlying physical logic. By generating spacetime distortion externally, the spacecraft itself can remain inside a protected interior region, isolated from the most extreme effects of the warp field. This observation attracted attention because it suggests that the Enterprise's iconic design aligns with physical constraints now being explored seriously in theoretical physics. While the ship was never intended as a scientific prototype, its structure mirrors solutions emerging from modern warp field modeling. The scientific importance of this research lies in how it reframes the long-standing discussion around warp drives. For many years, faster-than-light travel was largely dismissed due to extreme physical requirements, particularly the need for exotic forms of energy that have never been observed at usable scales. Rather than attempting to bypass these limitations, newer models focus on identifying where the true constraints exist. By refining the geometry of spacetime distortion, researchers aim to separate mathematical impossibility from unresolved theoretical challenges. One of the most important developments is the shift away from a single, continuous warp bubble. Dividing the warp field into discrete regions, such as separate cylindrical or nacelle-like generators, makes the equations more manageable and clarifies how spacetime distortion might be controlled. This geometric separation allows a clear distinction between the region where spacetime is manipulated and the region where the spacecraft and its occupants reside. This distinction has important implications within the theory itself. Earlier warp drive concepts raised concerns about instability, intense tidal forces, and unpredictable effects within the warp bubble. Externalizing the field generators introduces a clear conceptual boundary between distorted spacetime and a stable interior zone. In this context, the Enterprise's design appears unexpectedly consistent with modern theoretical thinking. Its external warp nacelles isolate the engines from the crew compartment, a configuration that aligns with how researchers now conceptualize safer warp field arrangements. Researchers emphasize that these developments remain theoretical. No experimental warp drive exists, and no known technology can generate the required spacetime distortions at any meaningful scale. However, the work demonstrates that warp drive concepts can be explored within rigorous mathematical frameworks, rather than being dismissed as purely fictional. This matters because it changes the status of warp drives within physics. Instead of being treated as impossible, they are increasingly viewed as long-term theoretical problems, similar to how concepts like gravitational waves once existed only on paper before later experimental confirmation. In that sense, this research represents progress not toward immediate applications, but toward clearer understanding of what physics allows and where its limits may lie. The implications of this research extend beyond the question of faster-than-light travel itself. Even if warp drives remain unattainable for the foreseeable future, these studies contribute to broader discussions about spacetime engineering and advanced propulsion theory. One implication concerns spacecraft design realism. If warp-like systems were ever developed, they would likely require extended structures and externally positioned field generators rather than compact, internally contained engines. This challenges many popular depictions of futuristic spacecraft and provides clearer constraints for theoretical exploration. Another implication involves experimental research. While creating a full warp bubble is far beyond current capabilities, scientists continue to explore whether extremely small spacetime distortions can be detected under laboratory conditions. Interferometry experiments, for example, aim to measure subtle curvature effects at very small scales. These experiments do not attempt to create warp drives, but they help determine whether spacetime manipulation can be observed and quantified. Advances in quantum physics may also play a role in shaping future research. Some theoretical discussions connect exotic energy requirements to quantum vacuum phenomena. While these effects are currently minuscule and difficult to control, better understanding them could influence how physicists think about spacetime manipulation in the long term. Beyond technical considerations, this research highlights the broader value of speculative science. Many ideas that once seemed impractical were refined through decades of theoretical work before experimental validation became possible. Studying warp drives pushes physics to examine the boundaries of general relativity, energy conditions, and spacetime geometry, even if no immediate applications emerge. There is also a cultural dimension. Star Trek did not provide technical solutions, but it offered a conceptual framework that encouraged scientists to think beyond conventional propulsion. That influence continues to shape how ambitious ideas are approached today. Rather than proving science fiction correct, this work illustrates how imagination and physics can interact productively. Fiction raises questions, and science determines which of those questions remain open. Warp drives remain theoretical, but recent research suggests some science fiction designs reflect real physical constraints. The Enterprise's external engines align with emerging ideas about spacetime geometry and field placement. This doesn't bring faster-than-light travel closer, but it sharpens how scientists explore what might be possible.